So let's take a look at examples number 25 and 26 here to get a little more information about removable and non-removable discontinuities. In regards to the example 25 here, we have f of x equal to x squared minus 4 over x minus 2. What's the domain of our function? So take a second and figure out what the domain is. That's correct. It's going to be all real numbers except x cannot be equal to 2. If x is equal to 2, we are dividing by 0, and we have an issue with that. Okay. What's the limit as x approaches 2 of the function? Well, we're interested in the limit as x approaches 2, and here's our function right here. If we plug 2 into our function, we're going to get 0 in the numerator and 0 in the denominator. We're going to get the indeterminate form, which means that we can look to simplify it. And in fact, by simplifying the numerator, by reverse FOILing it there, we have that situation of x plus 2 times x minus 2 in our numerator. We can eliminate the x minus 2's, and now when we plug in our 2, we see that the limit will be equal to 4. Right. So can we redefine our function? And here's what it means to redefine. We're going to turn our function, which right now is just a rational function, into a piecewise defined function. Okay, so yes, we can redefine this. We're going to have f of x is equal to, and then there's our little open brace that symbolizes a piecewise defined function. And the function is going to behave like this. X squared minus 4 over x minus 2 when x is not 2. Okay, oops, that's off the screen there. Hold on a second, let me get that back. All right, there we go. All right, x is not equal to 2. We can follow this function, okay? But we have an issue when x is equal to 2, okay? And that issue is that we're trying to divide by 0. But we know that the limit as x approaches 2 is 4. So if the function's value is 4 when x is 2, then we're going to have a nice continuous function. We're redefining the function where we had the issue. The issue is at x equals 2. So when x is 2, we want the value of the function to match right up and be nice and smooth. Okay? Well, the value of the function as we get close to 2 is 4. So if we make the function equal to 4 when x is 2, then we will not have that hole in the graph. That hole will be filled in by that dot right there. In regards to problem number 26, all right, what's the domain of our function now? We have x plus 3 over x squared minus 9. Well, we have an issue where we don't want 0 in the denominator, and there's two values of x which make this true, 3 and negative 3. Negative 3 squared, remember, is 9. 9 minus 9 is 0. So our domain is all real numbers, but x cannot be 3 or negative 3. Okay. So what's the limit as x approaches 3? Well, we have to do the same thing that we did right up here. All right, so we are going to factor our denominator, and we're looking at the limit as x approaches 3 of x plus 3 over x plus 3 times x minus 3. Right? And we can eliminate the x plus 3's like we did in the previous problem, but if we plug 3 into this, we still have a 0 in the denominator. So the limit does not exist. Okay, we have a vertical asymptote happening there, right? Because we still are dividing by 0 after we removed our issue. Okay, so the issue that we removed is in terms of the limit as x approaches negative 3, right? Because by doing this exact same thing here, the limit as x approaches negative 3 of x plus 3 over x plus 3 times x minus 3, well, those cross out to 1. And when we plug in negative 3 minus 3 more is negative 6. So we have a 1 in the numerator and a negative 6 in the denominator. All right, so can we redefine this function? Well, unfortunately, we cannot. If our only issue was at x equals negative 3, then yes, we would be able to redefine the function to be equal to negative 1/6 when x is equal to negative 3, just like we did up here. But we can't get around this issue of the limit not existing when x is equal to 3. So can we redefine? No, we cannot. We have a non-removable discontinuity when x is equal to 3. There's nothing we can do about it. That's the difference between removable and non-removable. Can we redefine the function to fill in the dot, or do we have a vertical asymptote where there's just no way that we can make the connection and to give ourselves a continuous function?